Hello everyone. So previously we had discussed on the this one Chinese remainder algorithm, right? So Chinese remainder theorem algorithm basically. Yep. So today let's discuss one of the this one interesting algorithms as well, named Euler's Totient function. Yeah. So what does this algorithm states? Let's get into the definition part. Yeah. So let's see what it states here. So Euler's Totient function, denoted as, this one is nothing but the totient of n, right? So this one totient of n. It counts how many integers from 1 to n are co-prime to the n basically, right? So what it does, it counts how many integers from 1 to n are this one co-prime to n, right? That is nothing but numbers whose greatest common divisor or GCD with n is 1. Yeah. So here Euler totient function, denoted as this one totient of n, counts how many integers from 1 to n are co-prime to n, nothing but this one numbers where greatest common divisor or GCD with n is 1. Yep. In simple words, it tells how many numbers less than or equal to n, right? How many this one numbers less than or equal to n share no common factors with it other than the one. Yep. So let's get into the definition part, man. This looks interesting actually. Let's get into the definition part. The key property of Euler's totient function is if n is equivalent to the p1 to the this one to the power of a1 into p2 to the power of a2 into, finally we have been given here, into pk to the power of ak, right? So where p1 p2 up to pk are distinct prime factors of n, right? Then totient of n is equivalent to, so this one n into 1 minus 1 by this one p1 into 1 minus 1 by p2 into 1 minus 1, last one is nothing but the pk, right? So this is fine. Yep. Simple. Now let's go with a simple example here. Suppose n equals 10, that is equivalent to the 2 into 5, right? That is equivalent to the 10. We have considered 10. That is equivalent to the 2 into 5, right? So then totient of 10 is nothing but, so we have to go with this formula, man. N into 1, this one 1 minus 1 by p1 into 1 minus 1 by p2 into, finally, 1 minus 1 by pk, right? So this one will be 10 into 1 minus 1 by 2 into this one 1 minus 1 by 5, because we are going with 2 into 5 here, right? So this is fine. Where did I stop here? Yeah, 1 into this one 1 minus 1 by 2 into 1 minus 1 by 5, that is equivalent to actually 10 into 1 by 2 into 4 by 5, right? So this is equivalent to the 4 actually. In simple terms, we have to get the output 4. Yeah. So there are this one 4 numbers actually that are co-prime with 10, nothing but, so between 1 and 10 we have this one, what do we call, the prime numbers are actually from 1 to 10. The prime numbers are 1, 3, 7 as well as the 9. Yep. So simple one, right? So I have shown you with the example as well. So all we have to know is this formula actually for, and these things actually. If n p1 to the power of a1 into p2 to the power of a2 up to p2 to the power of pk to the power of ak, right? So where p1 p2, so this one we have already discussed, this is fine. So this one, this formula is very important actually. Yeah, totient of n equals n into 1 minus 1 by p1 into 1 minus 1 by p2 into up to this one 1 minus 1 by pk. Yep. So this is fine, man. Now let's try to implement, or let's try to articulate the same thing in the form of code. Yep. So let's do one thing. Let me go with the function here, Euler totient. Yep, Euler totient of n. So this is fine. Now within this function, let me assign result, or let me assign result to n. Nothing but we'll be starting with the n actually. Let me initialize p to 2. Why we are initializing p to 2? 2 is the smallest prime, right? So that is the reason here. See, somewhere. So yeah, n equals to 10, we considered actually 2 into 5, right? 2 is the smallest prime actually. Yep. So this is fine. Now let's go with the while loop. In simple terms, let's loop through all the primes up to square root of n here. So I'll just go with while of this one Python, right? So I'll just go with a p into p here. If it is less than or equal to n, then what shall we do? Let's write the simple if condition. If p divides n, then it's a prime factor, right? So this one I'll just go with n modulo p, if it is equivalent to the 0, if it is equivalent to the value 0, meaning we have to remove all the occurrence of this particular prime, right? So n equals n by p is what we have to write. So I'll just go with n equals n by p. So this is fine, man. Next, let's do one thing. Next, let's do one thing. Did I miss something, man, here? If n modulo p, this one equals 0, this is fine, actually. So I completely forgot the while loop here. So we have to remove all the occurrences of this prime, right? So I said it, but I didn't type. So this one, while n modulo p actually, if it is equivalent to the 0. Yep, so this is fine, man. Let me cut this one here. So I'll just keep enter. So let me paste this one over here, right? So this is fine. If condition before the while loop, nothing but the line number, this one 32, it's just that if p divides n, then it's a prime factor, right? If n modulo p equivalent to the 0. If p divides n, then it's a prime factor, right? So don't get confused here. Finally, what we have to do, we have to apply the formula result equals result into 1 minus 1 by p that we have discussed, right? So I'll just go with here result, 1 second. So let me go with here result equals result into uh, we have to go with the result equals result minus, right? I got confused here. So this is fine. So this one will be result by p actually. So here nothing but if you remember this one 1 minus 1 by p we are going with, right? So result equals result into 1 minus 1 by p we are going with. So yep, so this is fine. The next step, what we will be doing here. So we have to move to the next potential prime, nothing but p equals p plus 1. Yeah. So the next step would be if any prime is greater than square root of n, if any prime is greater than this one square root of n, then it remains, right? So here if n greater than 1, then I'll just go with the result. So we'll be applying the formula for the last prime factor here. Result equals result minus result by n actually. Result by n, right? So this is fine. The next one or the final line here would be we have to return the final totient value. Nothing that is stored in the resulting variable result actually, right? So let me return here result. Yep. So this is it for the this one algorithm. Very simple one. Yeah. So whatever we discussed in the explanation part, exact thing we have articulated in the form of code. Simple. Now let me go with the this one example usage. So I'll just go with the n equals 10. So here we have n equals 10 itself. For the example, we have considered this one, right? So this is fine. So let me print something for the interactive purpose actually. We have to show the output, right? So I'll just go with here for the totient. So we cannot type this one. Let me copy this one instead. Yep. Totient of. So I'll just go with here, comma. So this is fine. Let me pass n as well here, n, comma. So I'll just close this one over here. So this is fine. Next, what should I do here? Did I do something wrong, man? No, right? So here, this is fine. I'll just go with Euler totient here. Let me pass the n. Euler totient of n. Yeah, nothing but 10 in our case, right? So this is fine. So we have already discussed this one, Algo. Let me explain this one again. So that we don't forget the algorithm, right? So result equals n here. So this one we are starting with the assumption totient of n is equivalent to the n, right? So next we are initializing p to 2, nothing but the smallest prime number to begin checking is 2. We know this one, right? So next we are going with the while loop, the line number 31. So we are going with the while loop, while p into p less than or equal to n, nothing but no need to check beyond square root of n for the prime factors. Yep, we had discussed this one. If n modulo p, this is equivalent to the 0, meaning when p divides n, then it's a prime factor. Next, we are going with a while loop here. While n modulo p is equivalent to the 0, n equals n by p, nothing but we are dividing out all powers of this particular prime. Yeah. Next, we are going with the result. Yeah, result equals result minus this one result by p actually. So we are just applying the totient of n formula, this one adjustment for that particular prime, this one actually, yeah, totient of n, this formula we have already discussed this one. The same thing we had applied for n equals to 10 here, right? The same thing. Yep. So next we are going with a this one. What do we call? If n greater than one, sorry, here this one line number 37. After loop, if there is a remaining prime factor, then result equals result minus result by n we are given. Nothing but we are applying the adjustment for that particular last prime, right? Next, finally, what we are doing, we are just returning the result, meaning we just have to, or we are just returning the computed totient value in simple terms, right? So printing here, this one, basically n equals to 10. For n equals to 10, we have to get the output 4, because the prime numbers bit from 1 to 10 are this one 1, 3, 5, and 7 respectively. So we have to get 4 numbers, right? 1, 3, 7, and 9. So overall, this one we are calculating overall how many numbers that are present from 1 to 10 we are calculating, and we are displaying in the form of output. So we have to get the output 4 here in this case, right? So totient of 10, we have to get the output 4 actually in simple terms, right? So see, if I run this code, numbers less than 10 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Less than or equal to 10 we have to consider accordingly with the while loop, right? So now numbers co-prime to 10, nothing but GCD is GCD equals 1, right? Numbers co-prime to 10, nothing but when GCD equals 1 are 1, 3, 7, and 9 respectively. So total equals 4 we have to get. Total equals 4. So totient of 10 here, in this case, totient of n we have passed 10 here. Totient of 10 we have to get the output 10 itself. Sorry, 4 actually. Yep. So let's check the same here. So let me copy this one entirely. I'll just come here. I'll just give Control J. Let me type Python followed by the file name.py. We have the error here, man. N modulo 0 equals 0. Where is this? Line number 33. Eh? This one. We are going with a while loop actually. So this is fine. Next, we are going with this one. N modulo p equals 0. So this one has to be while n modulo p actually. I have given 0 here. Sorry. N modulo p equals 0. Right. So while loop, right? So we are just removing all the occurrences of this particular prime, basically, of the particular prime, basically here. Right. So let me give clear screen. Let me run this one again. Now see, totient of 10 is equivalent to the 4. So let me do one thing. This is fine. Totient of 10 equals 4. We are getting the desired output, right? As discussed, right? So yep. So this is it for the all code, right? Simple one, very simple one. Now let's do one thing. As we have complete idea on the Euler's Totient function algorithm, let me summarize whatever we have learned so far. So we have to know this 4 to 5 points actually. These are very important. Just try to listen to this. Yeah. So Euler's Totient function basically, so represented by this one, quotient of n. So this counts the integers less than or equal to n. This counts the integers less than or equal to n that are co-prime to n. That are co-prime to n actually. Yeah, that are co-prime to n actually. Yeah, so this is fine. Next, the second one is formula is, so we are going with here totient of n equals n into, so we can just call this one as big pi actually. So I can just represent in this way, right? This one will be big pi 1 minus 1 by p actually, right? So 1 minus 1 by p1 into 1 minus 1 by p2 into 1 minus 1 finally up to 1 minus 1 by pk, right? So we can just write it here pi by 1 minus 1 by p actually for each distinct prime factor, this one p of n basically. So this is the formula. Yeah, we have to know this. So entire algorithm is based on this particular formula itself. Yeah. So this is fine, I believe. So this is mainly used in, let's discuss some of the this one use cases. Actually, this is mainly used in cryptography, right? So this is mainly used in cryptography, nothing but RSA algorithm. Also, we make use of it within the modular inverses as well. So let's go with here modular inverses, and let's go with the number theory as well. Yeah, let's go with the number theory as well. So we'll be making use of it within the cryptography, modular inverses, and the number theory as well. Yep. So this is fine. So now let's move on with the last part, nothing but discussing the time complexity and the space complexity. So what will be the time complexity and the space complexity for the algorithm that we had discussed so far actually? Nothing but for the Euler totient function algorithm, time complexity would lead to big O of square root of n. Yeah, overall time complexity would lead to big O of square root of n, and space complexity would lead to big O of 1, right? So the time complexity and the space complexity for the algorithm that we had written or that we have written is big O of square root of n and big O of 1 respectively. Yeah, so these are some of the points that I found this one very helpful, right? Very helpful. Yeah, you have to know this at any cost, man. Yep. If someone says Euler totient function, this one or this one Euler totient function algorithm, you have to be uh, you have to remember these parts actually suddenly. Yep. So this is completely based on this particular formula itself, as I've said. Yep. So this is fine. Let me delete this one. So we are done with the Euler's totient function algorithm. Yep. So this is fine. Next, what shall we discuss? Which algorithm? So we are left with some four algorithms actually. Tomorrow, we'll be discussing about the Miller-Rabin primality test as well as the Pollard RHO factorization algorithm. Yep, so these two algorithms basically. Again, so tomorrow we'll be discussing on the this one topics Miller-Rabin primality test algorithm as well as the Pollard RHO factorization algorithm. Yep. So and we are left after that one we are left with only two algorithms, nothing but fast Fourier transform algorithm and the number theoretic transform algorithm, right? So let's just this one speak about the tomorrow actually, as we're done with today's algorithms actually, discussing today's algorithm. So tomorrow we'll be discussing on the topics this one Miller Rabin primality test algorithm as well as the Pollard RHO factorization algorithm. Yep. So for now, this is it. Thanks for watching, guys.